Okay, so let's solve one initial value problem. Okay, so what do I mean by initial value problem? Let's take one example. So suppose differential equation is y prime is equal to minus 2xy, and the initial value condition is y0 is equal to 1.8. So it means that at x is equal to 0, the value of y is 1.8. So this equation is a separable equation. So what I can do is I can take y on the other side. So it will become y prime divided by y is equal to minus 2x. And then I can write it like this. Y prime is dy over dx. So it is dy over dx. But dx I take on the other side. So it will be minus 2x dx. And then for solving it, I take the integral on both sides. So it will be minus 2x dx. Integral of 1 over y is log of y, and that is equal to, over here it will be minus 2x square over 2 plus a constant. So in this case, log of y is equal to minus x square plus constant. Or if I want to remove log from here, I will take the exponentiation of both sides. So take the exponent of both sides. So it will be y, okay, will be equal to e power minus x square plus c. Okay, and I can further simplify it, because e power minus x square plus c is same as e power minus x square into e power c, and e power c in turn is also another arbitrary constant. So I can take e power c is another constant. Okay, so if I say it as c1, so that arbitrary constant I can take it as c e power minus x square. So e power c1 is an arbitrary constant, which is also equal to another arbitrary constant c. Okay, so this is the general solution of the differential equation. So now I can apply the initial values. So which means that I will put x is equal to 0 and y is equal to 1.8. So this will give me the value of c. So 1.8 is equal to c into e power minus 0 square. So e power minus 0 square is of course 1. So 1.8 is equal to c into 1. So this means that the value of c is equal to 1.8. So the particular solution for this initial value problem is then this y is equal to 1.8 e power minus x square. So as a modeling example, let's take the example of radio carbon dating. Okay, radio carbon dating, which means that it is actually a method. Okay, it is actually an analytical method. It is a method by which age of old species can be determined, so such as the age of fossils, etc. Okay, before this example I did solve this equation. Okay, so the solution of the solution which will be involved, So the solution which we will be using for this kind of modeling problem will involve the exponential function. Not similar to this, but not exactly exactly this function, but it will be similar. So let me just tell that. So what that radiocarbon dating example, what we can do. So this radiocarbon dating example comes from the observation that the uh, the the decay in the radiocarbon, that means radioactive element, depends on the quantity of the radioactive substance. So for example, if I take the uh, rate of change of quantity of the radioactive substance with respect to time. So for example, if I take, say, Y is the radioactive substance, okay, Y is equal to the amount of radioactive substance. So the rate of change of that substance will be proportional to the quantity of that substance. Or in other words, if I can say that dy over dt will be equal to ky, where k is the proportionality constant. So this type of equation is a separable equation. The solution of this equation is similar to the above. So in this case, the solution will be y is equal to the proportionality constant times e power k t. Okay. I'm not giving you the solution but the solution is similar to the previous example. Okay, so you can solve that. So this is the general solution. So now let's suppose that the half-life of carbon C614 is 5,715 years. Okay, so what does it mean by the half-life? I think from your physics, you know that half-life is that number of years in which the quantity of the radioactive substance in a radioactive element becomes half. Okay, so this is so what is this C614? Actually it is a carbon is generally not a radioactive substance, but that carbon which is not radioactive is C612. Okay, so C612 is the normal carbon, okay, with the 12 atomic mass, but with 14 atomic mass, that type of carbon is a radioactive carbon. So it gradually converts into C12. Okay, but of course one thing is that this radioactive carbon is very minute quantity, and it's quite scarce. But but it has been found that this radioactive carbon is present in some living organisms, and then as long as the organism is live, the ratio of this radioactive carbon to the normal carbon does not change. But as when that organism dies, then there is a change of this ratio from the radioactive carbon to the normal carbon. So as an example, if a fossil was found, okay, if a fossil has about 52.5% of original C614 left. Okay, if a fossil has 52.5% C614 left, but how do we determine it? Of course, this is not the domain. This is not our domain. For this we need to have some knowledge about physics and nuclear physics, etc. So there will be some methods that will determine that in a fossil some 52.5% of the original carbon C6 carbon has left. So that means originally it was 100%, so now it's 52.5%. So now we need to determine that how old is that fossil. So from this information we need to determine, and then we have this general equation over here. So and this for this general equation we have actually two unknowns, C and K. First we can determine the value of we can input some of the information into that, and then we can find the value. So what we can say, what we can do over here is that we first of all we apply this information of half-life. Half-life means if the original for example, if the original value of the radioactive substance was Y, so then after half-life it will be 0.5 Y. Okay, so from this information, if you put it over here into this equation, so the value of Y was at what time? At time 0. Okay, the value of Y was at time 0, and the value of 0.5 Y will be at time equal to 5715 years. Okay, so if I input these values over here, so for example into this equation, so I will put 0.5 Y, okay, 0.5 Y is equal to C into e power 5715 t. So I have actually two unknowns over here. So this equation does not give me much information over here, but what I can do is I can. So actually this equation 0.5y is equal to C 5715t has two unknowns. Okay, we can keep this equation for now, but let's apply another equation. We know that at time t is equal to 0, what was the value? That will be the initial value. Okay, so let's take that the initial value was y0, which is another unknown. So it will be like y0 is equal to C and then e power k and times t. Okay, k times 0. In fact, let me make some correction over here. It should be e power, the value of t was 5715 k. Okay, but from here what we can find is that C, the value of C is equal to y0. Okay, because e power 0 is 1, so this term will be 1, and then C will be equal to y0. So from here, in fact, what we can put is that if the initial value was y0, then we can put y0 over here, and then we can similarly we can put y0 over here. So now we can use this relationship over here in this term, in this equation. So 0.5 y0 is equal to y0, because C is equal to y0, our e power 5715 5715 k. Okay, so from here we can find the value of k, because y0 will cancel with y0. So from here we can find the value of k will be equal to minus 0.0001213. Okay, we will continue this problem in the next video.